Assalamu alaikum warahmatullahi wabarakatuh. So in today's video we will start with the synchronous motor. Uh, so synchronous motor is a machine that actually has the capability that it will run on the synchronous speed, and remember that either it can run at synchronous speed or it will not run at all. So the synchronous speed, as we all know, is ns equal to 120 f by p. So depending upon the frequency of our power system, and the number of holes in the design of a machine, the synchronous frequency will be fixed. So synchronous motors are, the important thing is that they are not self-starting. So obviously we need some external force to bring them near the synchronous speed so they can catch up for the synchronous speed. Now, the most important use of the synchronous motor is because of its capability of running at different power factors. So it can either be as a work as a lagging power factor, means it can run it will act as a load of lagging power factor, or as a leading power factor, or it can be used for the unity power factor. So it can be, we can control the power factor of the synchronous motor somehow, that we will look in the future as we will go along this chapter. So it can be either as a lagging, leading, or unity power factors. So sometimes actually most of the times the synchronous motors are used for the power factor corrections. There are other methods to improve the power factor is by using the capacitor banks. So this is the structure. The structure of basically the synchronous generator and synchronous motor are it's approximately same. They have this stator, which actually, when we provide the three-phase supply to this stator, so it will produce a rotating magnetic field in this machine. Also, we have this rotor, which we have to supply the DC to produce the field current. If we don't have the DC for the field current, so it cannot rotate at all. But obviously, as we have said previously, that we need certain method to attain this synchronous speed. Otherwise, motor will not run by itself. So again, we have this target used is K times PR cos product with BS, and that would be counterclockwise. So let's assume a two-pole synchronous motor, and we have two magnetic fields present in the machine, as we have the stator magnetic field and the rotor magnetic field, because at the stator we are providing the three-phase supply, and we have the rotating magnetic field, and on the rotor we have the DC supply, which is producing the uniform magnetic field. And IF is responsible for producing the magnetic field on the rotor. And we have the three-phase stator, and so three-phase stator cores of the machine, and we will have the rotating magnetic field of the stator. So BR will obviously tend to line up with BS. So BR will tend to line up with BS. So it will try to catch this BS just as two bar magnets. As BS is a rotating magnetic field, and BR and the rotor itself will constantly try to catch up. So the larger the angle between the two magnetic fields, up to a certain maximum, the greater the torque on the rotor of the machine. So this angle will produce the torque. But remember that the speed of the rotor will be the same as the synchronous speed. So basic principle, rotor chases the rotating stator magnetic field around in a circle, never quite catching up with it. So since the synchronous motor is the same physical machine as synchronous generator, all of the basic speed, power and torque equations of synchronous generator apply to the synchronous motor also. So this is very important thing that you remember. Do not confuse with the angle between BR and BS. This is the angles between the rotor magnetic field and the stator magnetic field. But the stator and the rotor itself will be rotating physically at the synchronous speed. So do not confuse the angle, means if they are not aligned with each other, so they will not tend to align with each other, because if they will align to each other, so this will be BR cos BS, so that will be BR BS sine theta, so the angle should be there. So if sine theta is 0, so there will be no torque. Now this is the same so equivalent circuit of the synchronous motor. The only difference is that the IA is in opposite direction. In the synchronous generator, we were having the power from the generator, but here in the synchronous motor, we are providing the power to the stator. So except that the direction of power flow is obviously reversed, because now we are providing the power to the stator. Since the direction of the power flow in the equivalent circuit of a synchronous motor is exactly the same as the equivalent circuit of synchronous generator, except that the reference direction of IA is reversed. So you can see here IA is reversed. In synchronous generator, it's in the opposite direction. Okay, you got it? Because we are having the power to the load. We are giving the power to the load. Now we are having the power from the source. So in this way, the equation will be simply, in the generator, we had these negative signs. Now here we have these positive signs. So V phase will be equal to induced voltage plus JXSIA plus RAI. Similarly, we can have the EA from this equation. So this is the per phase equivalent circuit. So on the rotor side, we have the same. We can have this RF to control the current, IF, and this is the rotor winding. So we have applied this field voltage. So this is a three-phase equivalent circuit of this synchronous motor. So we have this one phase, second phase, and third phase. Now, the synchronous generator has a prime mover turning its shaft, causing it to rotate. The direction of the applied torque and the prime mover is in the direction of motion, because the prime mover makes the generator rotate in its first place. So BR, which is used to produce EA, B net is used to produce phase voltage, and BS produce the E stator, which is JXSIA, which involves the armature reaction and other losses due to the inductance. So the rotation of both the phasor diagram and magnetic field diagram is counterclockwise, following the standard mathematical convention of increasing angle. The induced torque in the generator can be found from the magnetic field diagram. So here we have taken the B net and the angle between BR. So torque is equal to K times PR cross per B net. K is equal to PR B net sine delta. So the induced torque in this machine is clockwise, opposing the direction of rotation. In other words, the induced torque in the generator is counter torque, opposing the rotation caused by the external applied torque. While now if the prime mover suddenly loses power and starts to drag the machine's shaft, the rotor slows down because of the drag on the shaft and falls behind the net magnetic field in the machine. So as the rotor and therefore BR slows down and falls behind the B net, the operation of the machine suddenly changes. So what happens then? So when BR is behind B net, now BR is behind the B net, the induced torque's direction reverses. So the direction of the torque is changed. So and becomes counterclockwise. In other words, the machine's torque is now in the direction of motion. That's a very important point to understand. Now the BR is behind the B net, while in the generator BR was ahead of B net, and that was causing the clockwise rotation, or clockwise torque. Now because in the generator we had the external prime mover, now we have removed the prime mover. So it is rotating by itself. So obviously it will drag behind. Now rotor has no external power which is rotating it. Okay, now then it will the torque that will be produced will be in the opposite direction, and that opposite direction will be in the direction of motion. So the now machine is acting as a motor. So the increasing torque angle delta result in the larger and larger torque in the direction of rotation. So that obviously we know that the motor is used to carry a load, a mechanical load. Torque in the direction of rotation until eventually the motor's induced torque equal the load torque on its shaft. So obviously that's important thing. You must remember that the machine, either it's a DC machine, induction machine, synchronous machine, motor, so it will produce the same torque as the load is connected to its shaft. So now the machine is acting as a motor with synchronous speed. So this is the phasor diagram of synchronous motor corresponding to magnetic field. This is the magnetic field, and this is the equation that we have written for the generator. I hope you have understood so far how this synchronous motor works, the equivalent circuit. And still, if you have any questions, please feel free to ask. Assalamu alaikum wa rahmatullahi wa